Hey guys, welcome to Algo Forces. So today we'll be moving ahead with Leetcode problem 684, that is redundant connection. So I'll explain you the problem first, then we'll move towards the approach and then the coding part. So it is saying that tree in the given problem, tree is an undirected graph that is connected and has no cycles. So basically as you can see, this is the connected graph and you are given a graph that started as a tree with n nodes labeled 1 to n with one additional edge added. The additional edge has two different vertices chosen from a 1 to n and was not the edge that already existed. The graph is represented as an array edges of length n where edges equals to a of I, b of I indicates that there is an edge between nodes of ai and bi in the graph. So as you can see, you'll be given an array edges and here you'll be given few nodes. So in this graph, what they want to say is, so initially it is a tree, but they have added one edge. So we have to find out that edge which is extra. Okay, so that is the redundant edge, right? If we remove that edge, then the graph would be a tree. So this is what the problem is, and if it might happen that there are multiple edges that can convert the tree into the graph. For example, here if we can remove 1 3, then also this graph will be converted into a tree, and similarly 2 3 can also be such case, and 1 2 is also such case. So in this case we have to return the answer that occurs last in the input. Okay, so let's move to the approach. Okay, so let's consider this graph 1, 2, 3, and 4 and 5. These are the nodes here. So, how do I find the redundant edge in this graph? Okay, so let's start to find out that which all components are connected. So, here 1, 2 is connected for sure. Okay, so now comes the edge 2, 3. So, 2, 3 is also connected. Now comes the edge 3, 4. 3, 4 is also connected. So, can you say that this all the nodes are connected from here? Yes, right. So, now comes the edge 1 and 4, but since you can see that 1 2 3 and 4 are already connected, so you cannot consider this edge and you have to return this. So how to find out that which all graphs are already connected? So basically here they are forming a group, right? So which is the algorithm used for grouping the nodes? So if you remember, for the grouping of nodes we use union find algorithm. So in that what we will do is we will group all the nodes which are connected, and if there is any edge which comes, like for example 1 and 4, and we have to find out that are these nodes 1 and 4 already part of some connected group. If yes, then we'll directly return this edge. So in Okay, so now how to apply the union find? So let's consider 1 and 0 in this, sorry, 1 and 2 in this case. So this is 1 and this is 2. So in this case I want to I want to do the union of these two nodes, that is I want to group these two nodes. So what I'll do is I will mark the parent of 2 as 1. So here 1 is one's parent is 1 only, but two's parent also becomes 1. So I'll just directly have this directed edge which specifies that two's parent is 1. Okay, so here this parent is 1 and here the 2's parent is also 1. Now I want to perform the union find of 2 and 3. Okay, so you can see that 3's parent is already 1. Sorry, 2's parent is already 1 and 3's parent is 3 itself as of now, as it is not connected with any other thing. So in this case, instead of instead of marking two's parent as 3, I will mark three's parent as 2, because 2 is already connected to 1, right? And we have to maintain this connection. We have to just add 3 in the group of 1 and 2. So in this case, I will just mark three's parent as 1 instead of 2. Okay, because 2's parent is already 1, that's why we just copy the parent of 2 in here. And also I have to add the group, add the 3 in this group. So in this case I will give another edge here marking 3's parent is also 1. Okay, so now comes 4. Now I have to group 3 and 4. again 3's parent is 1 and 1 is already connected to to two different nodes, right? So instead of marking 3's parent as 4, I will mark 4's parent as 3. So and 3 has already one parent, that is 1, so I will mark parent of 4 as 1. Okay, so here and comes now 1 and 4. So as you can see, 4's parent is already 1 and 1 is already connected to three different components. So but here 1 has the parent 1 and 4 also has the parent 1. So in this case, if the parent of both the nodes on the edge are same, and if see here, one's parent is 1 and four's parent is also 1. Okay, so in this case you'll directly return this particular edge. Okay, so this is the whole algorithm. The time complexity we will discuss after the coding part, and I hope this is clear to you. So now we'll move to the coding part. Okay, so let's start by completing the union find data structure. I'll have a class union find. So basically we need two things here. So one array to find out that with how many components a node is connected, and the second array for maintaining the parent of that particular node. So I will have two arrays, parent, and I will also have one another array, rank. Okay, now I'll have the in the constructor I will pass n, that is the length of the union find. So I will have parent equals to new integer n. So n basically specifies the number of nodes which we are dealing with. And similarly, there will be one more, rank. So initially, the parent of each node will be the node itself. So I will just initialize the parent array, integer x to 1. We are starting from one node, node 1 here. It is node 1 to the edges dot length. Okay, 1 less than n and I plus plus. So parent of I equals to I. Now, initially each node is connected only one node, that is itself. So I will also have to add rank as one, initialize rank by 1. Okay. So this is the constructor. Now we have complete the union method. Sorry, find method first. Find, this will return integer. This will return the parent. Find integer node. Okay. Okay, so here if node is not equal to parent of node, then we will do something, otherwise we'll return the node, the parent. We will return parent of node. So if node equals to parent, then parent of node will be equal to node itself. Okay, but now if node is not equal to parent, so what we will do in this case, we will do a find, and we will just pass parent of node in this case. So and here we will also have to update this one, that is parent of node. So consider the case where one, see here, if the parent of 3 is 1, and here if we have to union, if we have to, and similarly, see, there are two things. If the parent of 3 is 1 and there is one more node which has parent 3, let's say it is like this. So basically 4 has parent 3 and 3 has the parent of 1. So in this case we have to also mark the parent of 4 as 1, because eventually the parent of 3 is 1 only, right? So we have to mark this as 1 instead. So in this case what I'll do is I will find out, see here in the code, so basically I'm finding out the parent of 3, then I'm finding out the parent of 1. So parent of 1 is 1 only. So where, as in when I get the parent of node is equal to node, so in this case I will just return 1, and here I will just mark parent of 4 as 1 while returning. So once I have updated all the parents, so afterwards I will just directly return the parent of node. So in this case I will directly return 1. Okay, now I have to complete the union method. So this will have two things, node 1 and node 2. Okay, so I have to get parent 1. I'll find the parent of both the nodes, and similarly for node 2 I'll just mark it as integer. Okay, now if parent 1, if the parents are equal, so I'll directly return. Okay, but otherwise if they are not equal, so I will have to check which is the node which is connected with, I mean which is having parent which is connected with more nodes. So I will check that if parent of 1 is greater than rank of parent 2. So in this case we can say that parent of 1 is connected with more nodes. So I will mark parent of parent 2 equals to parent 1. Okay, because since 2 is connected with more nodes, we will update parent of 1 with parent of 2 instead of doing vice versa. And I also have to update the rank parent 1 plus equals to parent 2. Sorry, it is supposed to be rank of parent 2. Okay, so here it simply means that if the parent 2 is, if the parent 1 is connected with more components than parent 2, then I will just mark the parent 2 as parent of 1, and I have to add that many more components to parent of 1. So this is done by updation of rank. Now else case if in this case parent of parent 1 equals to parent 2 and rank of parent 2 equals to rank of parent 1. Okay, now what if the nodes are equal, I mean the parents are, sorry, ranks are equal. So let's say if there is the case that 1 is also not connected to any other thing and 2 is also not connected to any other thing, or maybe if they are connected to equal things, so in that case I specifically would, my preference would be that I merge 2 with 1 instead of merging 1 with 2. So in this case I will go with equal to here. You can also go in else case, but you have to modify the code accordingly. Okay, so union is also complete, find is also complete. Now let's go back to the main method. So here I will directly just, first of all I need to create an instance of union find. UF equals to new union find, and in the length I will give edges.length plus 1, because since it is starting from 1, if I'll give it edges.length then it will go out of index, out of bound. Okay, so I will give it one more. Now I'll just directly loop through the edges, teacher edge in edges. Okay, so do I will check if uf dot find edge of 0, if it is equal to uf dot find edge of 1. If the parents are equal, then we can say that they are already part of some group. So in that case I will directly return the edge. Otherwise I have to do uf dot union, I have to merge them into a group, edge 0 and edge 1. Okay, so this is it. And now let's see if we have made any error, compile time error. Okay, this seems fine. Let's try and run it. Okay, we are missing a return statement. So the default scenario, I will just return an integer array of length 2. Okay, it will never reach this case, but we still have to return it. So now let's try to run it. Okay, and let's try to submit. Okay, it got accepted. Okay, so for the time complexity, let's just see the code. So basically here we are traversing through all the edges. So this takes order of n time, and again we are doing union. So for union, we are just performing one find operation and one union operation, and the time complexity of find operation is order of 1, because here see we are doing path compression technique. Path compression technique means, let's say, I'll just give you an example. So let's say the parent of 3 is 1, I'll note it this way, and parent of parent of 4 is 3, let's say parent of 4 is 3. So in this case, instead of mentioning it like this, I'll just compress it to 1. That is, I'm just mentioning the parent of 3 directly instead of writing 3 here. So the parent of 4 will be now 1, because initially the parent of 4 was 3 and parent of 3 was 1. So indirectly the parent of 4 becomes 1. So this is called the path compression technique. And so now if I want to perform find operation, so it would be order of 1 only, as I can directly access the parent of the 4 of the particular node basically. So the overall time complexity would be order of n itself, because the union is on constant time, and the space complexity will also be order of n, because in the union find data structure, we are using two different arrays for storing rank as well as parent. So this is the overall complexity of the solution. And if you have any doubts, to comment in the comment section. I hope you like and subscribe this video. Okay, then bye bye.